In this video, we're going to go over some practice problems from section 7.4 through 8.1 in our textbook. Now, starting with section 7.4 here, what we want to do is add or subtract to simplify the following radical expressions that we see here. Now, we learned in section 7.4 that we can only combine radical expressions that have the same index, so we're looking at the nth root, and the same radicand. Now, the radicand is going to be the value underneath our radical. So for all of these, as you can see, these expressions all have the same index. We have the fourth root, the third root, and the square root. So we're good there, but we can't combine them or add or subtract them until we have the same value underneath our radical. That would be the radicand. So the whole idea here is to rewrite these expressions so that they do have the same index and radicand and that we can go ahead and combine them. Now, the key to doing so is to simplify our radical expressions. So for example, this first one here, the minus 2 square root 8, this is not fully simplified because the square root of 8 can be simplified further. And similarly, for the second one here, the square root of 32 can also be simplified further. So that's what we're going to go ahead and do. We're going to rewrite these expressions by simplifying the radicals. So the square root of 8, this is going to be the same thing as the square root of 4 times 2. So splitting up 8 into its two factors, and we want to make sure that at least one of these factors is a perfect square so that we can go ahead and simplify it. Similarly, for our second expression here, we know that the square root of 32 can be split up into 16 times 2. Again, kind of strategically picking these factors so that at least one of them is a perfect square. All right, let's go ahead and keep simplifying this. This is the same thing as the square root of 4 times the square root of 2 using our product rule. Similarly, for our second expression here, this is the same thing as the square root of 16 times the square root of 2. So let's go ahead and keep simplifying. For this first expression, we're going to have negative 2 times 2. This is where we get the square root of 4 is the same thing as 2. And then we still have the square root of 2. We can't do anything further there. Let's do the same thing for our second expression. We know that the square root of 16 is going to give us 4. So we're going to have a multiplication by 4 here. All right, and then we have the square root of 2. Further simplifying, we're going to end up with minus 4 root 2 plus 16 root 2. Okay, now notice, now we have two radical expressions here, and both of these radical expressions have the same index and the same radicand. So at this point, we can now go ahead and combine them. So we can look at this and recognize that we have minus 4 root 2's, and we add 16 more to that. That would give us 12 root 2. Another way that we can look at this at is using our distributive property. So since both of these terms have a square root 2, we can go ahead and pull that square root 2 out. So like this here. All right. Now from here, what we can do is simplify our parentheses here. We have a minus 4 and a plus 16. That's going to give us a positive 12. And then this is being multiplied by that root 2. So you can go either way. We can think of it as like combining like terms. Since both of these have a root 2, we can go ahead and combine them, or we can go ahead and use this distributive property. Either way, we're going to get that we have 12 root 2's. All right, so let's look at the next two. These are very similar. Now we're looking at the third root. So again, we have two different radical expressions and we're trying to combine them. But again, we don't have the same radicand for either. So we're going to go ahead and simplify them to see if we can get the same radicand. Now, in this case, it's going to be slightly different because now we're dealing with a third root. So we want to strategically pick factors of our radicands here and split them up into two or more factors, where one of them is a perfect cube. So what I mean is, for this first one here, we have the third root of 16. This is the same thing as the third root of 8 times 2. And I'm picking 8 because I know that that is a perfect cube, and I know this is going to simplify nicely. Similarly here, I have the third root of 54. This is going to be the same thing as the third root of 27 times 2. 27 is a perfect cube. Using our product rule here, this is what this splits up into, just so we can see where these values are coming from here. All right, now the third root of 8 is going to give us 2. And the third root of 2, we can't simplify that any further, so we're going to leave that as is, at least for now. And then the third root of 27 is going to give us 3. And then again, we still have this third root of 2. So just to emphasize, we got 2 from the third root of 8, and we got 3 from the third root of 27. All right, Let's go ahead and keep simplifying. We're going to have 2 times the third root of 2 plus 12 times the third root of 2. Now, at this point, we have two radical expressions that we want to add together, and both of these expressions have the same index and the same radicand. So we can go ahead and just combine them. This is going to end up with, or we're going to end up with 14 times the third root of 2. Let's make that a little nicer. All right, and this would be our final answer. All right, let's look at this last one here. Now, this one is very similar, but now we're looking at a fourth root. And in this case, we have variables underneath our radical. So these are our radicand in this case would be x to the fifth power times y, and then we have x times y. So what we need to do is we need to rewrite these guys so that we have the same radicand for both of these expressions. So the first thing that we need to recognize, just like we've seen in the other cases, is that we're dealing with a fourth root. So since we have a fifth root here, this power is higher than this one. We know that this can be simplified. So let's go ahead and do that. I'm going to break up our radicand into several factors, and at least one of them hopefully is going to be a perfect fourth root. So what I mean is, we're taking the fourth root of this whole thing. I'm going to break up x to the fifth power as x raised to the fourth power times x. And then we still have this y here. And again, I'm doing that because we're dealing with a fourth root. All right. Let's do the same thing for this one. In this case, our radicand is fully simplified here because the powers of these guys are smaller than this 4 here. So we can't simplify this any further. So that tells me maybe I want to try to rewrite this one so that it looks exactly like this. Once I get that, I can then go ahead and subtract these two expressions. So let's keep simplifying this using our product rule here. So breaking up these factors, and I'm just going to leave this guy alone. Can't simplify it any further. All right, now something to note here, using our rational exponents, this is the same thing here. If we're taking the fourth root of x raised to the fourth power, this is the same thing as x raised to the fourth power raised to the 1/4 power. This is going to give us x to the 4/4, which just gives us x by itself. So because of that, that entire thing turns into x. So we're going to get 3 times x, and then we have the fourth root of x times the fourth root of y. I actually I'm going to combine these back together. I only split them apart because we did it for this first one, but actually keeping them together is actually how we're going to go ahead and subtract these two radical expressions. Notice this first one here, we have 3x times the fourth root of xy minus 2x times the fourth root of xy. Since we have the same index and the same radicand, this product of x and y here, we could go ahead and subtract these guys. I'm going to end up with 3x times this guy minus 2x times this guy. So this is just going to give me 1x times that guy. So it's going to be x times the fourth root of xy. And again, for these ones, if it's not as obvious, it might be easier to use the method of pulling out our radical expression. So this would be the same thing as 3x minus 2x times the fourth root of xy. In that instance, it might be more obvious here. By pulling out this guy from both of these terms, we end up with 3 minus 2x, which just gives us 1 more x. So this would be our final answer. Now, this brings us to section 7.5, where we're going to be looking at multiplying and dividing rational expressions. So let's look at this first one here. For 16, we're multiplying two radical expressions, and these are binomials. We have two terms. So we're going to go ahead and FOIL these guys. We know we need to multiply the first, the outer, the inner, and the last terms. So doing that, multiplying our first terms, we're going to get square root 3 times square root 5. Multiplying our outer terms, this is going to be 2 times the square root of 3. Inner is 3 times the square root of 5. And last is going to be 3 times 2, which gives us 6. All right, let's go ahead and simplify this a little bit further. Using our product rule here, we know that this is going to be the same thing as a square root of 3 times 5, all under one radical. So this is going to end up being the square root of 15. Then we have our remaining terms here. Now we actually can't simplify this any further. Remember, we can combine radical expressions if they have the same index and the same radicand. Well, in this case, we don't have the same radicand for these three radical expressions here, and we also can't simplify them any further to make that be the case, like we saw in the last several examples. So this would just be our final answer. All right, let's look at 49 now. In this case, we're taking this radical expression and dividing it by this one. Now we can't really go any further than that when we're dividing this, but we want to make sure that our denominator is rationalized. So what this means is we want to make sure that our radical expression is fully simplified. And we know that they're not fully simplified if we do have a radical in our denominator. So in order to get rid of that radical, we will rationalize the denominator. So this process, like I said, involves getting rid of this radical symbol. And what we're going to do then is we're going to multiply the top and the bottom of this quotient by something that'll get rid of this square root. Now we want to strategically pick that something. And in this case, what we're going to do is multiply by the square root of 5. And we'll see why in a moment, why we're picking this value. If we go ahead and multiply by the square root of 5, let's see what we have in our numerator. We're going to have 9 times square root 3 times square root 5. And in our denominator, we're going to have square root of 5 times the square root of 5. So let's go ahead and keep simplifying. Using our product rule, we know we're going to have 9 times the square root of 15 in our numerator. And in our denominator, we're going to have the square root of 25. Well, we know the square root of 25 is just 5, so we can rewrite this like this here. And that's as far as we're going to go. This is going to be our final answer. We can't simplify this any further, but we know that we're done here because our denominator has been rationalized. So let's look at another example of rationalizing our denominator here. Now, in this case, it's going to be a little trickier because now we're dealing with a third root, as you can see. But let's go ahead and rewrite this using our quotient rule. We're still going to have this minus out front, but our quotient rule says that this radical is going to apply to our numerator and our denominator. So due to this, this tells me that we need to rationalize this denominator because we have this third root. Again, our radical expressions are not going to be fully simplified if there's a radical in our denominator. But in this case, we need to multiply by something to get rid of this third root. In the last example, we multiplied by the square root of 25 because we knew, or sorry, we multiplied by the square root of 5 because we knew we would end up with the square root of 25, which just gives us 5. So we kind of got to pick something similar, strategically pick something to multiply the numerator and the denominator by to get rid of this third root. As you can see here, this can't be simplified any further. We have a square under our radical and we have a third root. But do you remember what happens when we have a 3 and a 3 here, or the nth root and the nth power here? They actually end up canceling out. So what we're going to do then is we're going to multiply this by something so that we are able to cancel it out with a third root and a power 3 here. And that something is going to be the third root of just y. And we'll see why this works in a moment. So if we multiply by the third root of y here, let's see what we end up with. In our numerator, we're going to end up with, we still have this minus out front. We're going to have the third root of 6xy. And in our denominator here, we're going to have the third root of y cubed. Now, like I was saying before, the third root of y cubed is going to be the same thing as y cubed raised to the 1/3 power, which just gives us y by itself. So due to this, we got rid of the radical expression in our denominator. Our final answer here is going to be, we still have this negative out front, and we're taking the third root of 6 times x times y all over just y. And we know this is our final answer here because we have rationalized our denominator. This is as far as we can go. This is our fully simplified radical expression. All right, let's look at one more example in this section here. Now, again, we're dividing two radical expressions, and we know this is not fully simplified because we have a radical in our denominator. The issue here, though, is that we have a binomial in our denominator. So we're not able to just multiply by, let's say, the square root of 2. That's not going to get rid of our square root in our denominator. Instead, we need to multiply by the conjugate of the denominator. And if you haven't already looked at this in the textbook, please do so, but I'll go ahead and write this here. Let's say we have a binomial a plus b. The conjugate of this would be a minus b. And on the other hand, if we have a minus b, the conjugate would be a plus b. What we're going to do then is we're going to multiply by the conjugate of this guy, and the idea is we're going to get rid of the square root in our denominator. So let's go ahead and do that. The conjugate of our denominator in this case is going to be 3 plus square root 2. So we need to multiply the denominator by this, and whatever we do to the denominator, we also have to do to the numerator. So let's go ahead and multiply this out and see what we get here. In this case, we're going to have 3 times the square root of 8 plus the square root of 2 times the square root of 8. All right. In our denominator here, since we have the products of two binomials, we're going to have to FOIL this. So we're going to have 3 times 3. That's going to give us 9. Then we're going to have 3 times square root 2, but then we're going to have 3 times positive square root 2. Then we're going to have 3 times negative square root 2. So that's going to cancel out. Then we're going to have negative root 2 times root 2. So this will be negative root 2 times root 2. Okay, let's keep simplifying this further. We're going to have 3 times the square root of 8 plus the square root of 16 over 9 minus the square root of 4. So using our product rule here, we'll keep simplifying. We know the square root of 16 is going to give us 4, and we know that the square root of 4 is going to give us 2. All right. Now, something else to note here, we can keep simplifying this. We know we're going to get 7 in the denominator, but remember, this is not going to be fully simplified here. We need to make sure that this guy is fully simplified by breaking it up into two or more factors, with one of them being a square root. So let's go ahead and do that. We know the square root of 8 can be broken up into the square root of 4 times the square root of 2. We have 7 in the denominator. This is going to give me 3 times 2 times the square root of 2 plus 4 all over 7. And then lastly, fully simplifying this, I'm going to get 6 times the square root of 2 plus 4 all over 7. So just something to note here, if you had, let's say, rewritten this as 3 times the square root of 8 plus 4 over 7, you would have technically been incorrect here because this would not be fully simplified. So just keep that in mind when you are answering the homework problems. All right, so we actually have one more example from this section here. Question 102 here. We want to write this quotient in lowest terms. So this should be fairly simple here. We have two terms in our numerator and one in our denominator. Now notice every single one of these terms shares a common factor of 12. So what we can do is pull that 12 out. And I'm going to pull it out just from the numerator, and we'll see why in a moment. If I pull out 12 from 24, I'm going to be left with 2. And if I pull out 12 from 12 root 5, I'm just going to be left with that root 5. Then we have a 12 in the denominator. And as you can see, since we have a 12 on the top and the bottom, these guys are going to cancel out. And I'm just going to be left with 2 plus the square root of 5. So this would be that original quotient in our lowest terms. All right, so in section 7.6 here, we're going to be solving equations with radicals. Now, the whole idea is to first isolate the radical and then apply the power rule for solving a radical equation. Now, the whole point of this power rule is to essentially undo the radical. So once we've isolated it, for example, if we have the square root, what we can do is square both sides of our equation to undo that radical. If we have the cube root, we can cube both sides of our equation, and so on. Now, something important to note though, the power rule does say that if both sides of an equation are raised to the same power, all solutions of the original equation with that radical are also going to be solutions of the new equation. However, the power rule doesn't say that all of these are going to be solutions to the new equation. So what we're going to have to do is definitely check all of our proposed solutions that we get when trying to solve the equations. So with that being said, let's look at this first one here. So we want to solve this equation. So we want to isolate this variable k. So like I said, the first step is to isolate our radical. So I'm going to subtract 2 on both sides of this equation. So I isolate just the radical for now. So then we can apply the power rule. So I have the square root of 5k minus 3 is going to be equal to negative 2. Now, what we might want to do is go ahead and apply the power rule, so square both sides of this equation. However, we have to pay attention to what this is telling us. This is telling us that the square root of something is equal to -2. But we know that this can never happen. We're never going to have that the square root of anything is going to be -2. So this is an example where this equation has no solution. So in this case, the solution set is going to be empty since the square root of anything will never be -2, and it will actually never be negative in general. That is our issue here. We're never going to take the square root of something and get that it is negative. Okay? So we do have to be careful when we're solving these equations here, figuring out what this is actually telling us in our rules for square roots. Okay, let's look at this next one, 18 here. Now, this one is a little trickier. We are going to get a real solution here, though. Notice we have radicals on both sides of our equation. So technically, the radicals are already isolated. We have one on either side of our equation. So let's just go ahead and apply the power rule. So if I have the square root on both sides, what I'm going to do is square both sides of this equation. Remember, whatever we do on one side of an equation, we have to do to the other. Luckily, we have square roots on both sides, so these should cancel nicely. If I have the square root and a square, the radical in the square is going to cancel out, and I'm going to end up with 4x minus 2 by itself on the left-hand side of my equation. Similarly, on the right-hand side, the radical in the square is going to cancel, so I'm going to have 3x plus 5. Now, this looks like an equation we're used to solving. Let's get all of our variable terms on one side and all of our constants on the other. So I'm going to subtract 3x on both sides of my equation to get those variable terms and add 2 to get those constant terms together. 4x minus 3x, that's going to give me 1x, and on the right-hand side, 5 plus 2 is going to give me 7. Now, this is also going to be our proposed solution, like I was saying before. We need to make sure that we check it. When we're applying this power rule here, this is not guaranteed that this is going to be a solution. Now, in order to check it, what we're going to have to do is plug in the solution back into our original equation. So we're going to have the square root of 4 times 7 minus 2 on one side is equal to the square root of 3 times 7 plus 5 on the other side. And we need to make sure that these are equal. Well, on the left-hand side, I'm going to get the square root of 26, and on the right-hand side, I'm also going to get the square root of 26. So this tells us that this is our solution. So our solution set is going to be x is equal to 7. All right, so let's look at this next one here. We have the square root of 5 minus x is equal to this. Now notice in this one, we already have that our radical is completely isolated, so that first step is taken care of for us. Now the next step that we want to do is apply the power rule. Since we're dealing with the square root, we're going to square both sides of our equation. Doing so, we got rid of the radical on the left-hand side. We're going to end up with 5 minus x is equal to x plus 1 squared, which is the same thing as x plus 1 times x plus 1. All right, let's keep simplifying. Again, we want to solve this equation, so we want to solve for x. So what we're going to have to do is expand this product here, and then try to combine like terms and potentially factor this guy. So we're still going to have 5 minus x on the left-hand side. On the right-hand side here, we're going to have x squared plus x plus x. So we're going to get x squared plus 2x plus 1. All right, now from here, like I said, we want to combine like terms. So what I'm going to do is I'm going to add x on both sides of the equation and subtract 5 on both sides of the equation. The reason being is because we have an x squared here, so this tells me we're dealing with a quadratic equation, and we know how to solve a quadratic equation by factoring. So once we factor, we then want to use our zero factor property. So in order to do that, I need to make sure that one side of my equation is equal to 0. I'm going to get 0 is equal to x squared plus 3x minus 4. All right, from here, like I said, we want to see if we can factor this and use our zero factor property. So if I want to factor this guy, notice this is going to be one of our easier cases because the coefficient of our square term is 1. So I need to find two numbers that are going to multiply to give me -4 and add to give me 3. So let's go ahead and write this out here. Multiply to give me -4. So this could be -2 and +2, but when I add those guys together, I'm not going to get a negative or a +3. So this tells me I probably want a +4 and a -1. This is because 4 times -1 is going to give me -4, and 4 minus 1 gives me that 3. We can go ahead and also FOIL this and make sure we end up with this original equation. So from here, let's use our zero factor property. This tells us that if the product of two things equals 0, then either this is going to be equal to 0, or this is going to be equal to 0, or both. So we're going to get two solutions here. So this tells me that x plus 4 is going to be equal to 0, or x minus 1 is going to be equal to 0. So my two solutions then are going to be x is equal to -4 and x is equal to +1. But like I said, we need to make sure that these are in fact solutions. These are actually only proposed solutions. So let me move this up a little bit so we have a little more room. These are only proposed solutions, so we do need to check them. So I'm going to plug -4 into my original equation. If I do so if I plug in -4 into my original equation, just to save space, I'm just going to tell you what that is, but I'm going to plug -4 into my x's here. Doing so, I'm going to end up with the square root of 9 is equal to -3. Now, this is not a true statement here, so that means this guy is not going to be a solution. Let's check this next one. X is equal to +1. If I plug that into my original equation, I'm going to get that the square root of 4 is equal to 2, which is a true statement. So this guy is our only solution. So our final answer is that our solution set is going to consist of x is equal to 1. All right, let's look at this last one in section 7.6 here. In this case, we're dealing with a cube root. So notice we already have that our radical is isolated on one side of our equation. So again, that first step is taken care of. What we want to do next is apply the power rule. Since I have a cube root here, I'm actually going to cube both sides of my equation. Doing so, I'm going to undo the cube root, and I'm just going to be left with the radicand, so p minus 1, and on the right-hand side, I'm going to get 8. Okay, so in this case, this was actually fairly simple. I'm going to add 1 to both sides of my equation, and I'm going to get that p is equal to 9. Now again, this is just a proposed solution here, so we want to go ahead and check it. We're going to plug 9 into our original equation here. If we plug 9 into our original equation, we're going to get the third root of 9 minus 1 is equal to 2. We know this is a true statement because this is the third root of 8 is equal to 2, which is true. So this is going to be a solution here, and our solution set is going to consist of x is equal to 9. So this would be our final answer here. Got the curly braces. All right, so in section 8.1, this is going to be the last section of this video. We're going to be looking at the square root property and completing the square to solve quadratic equations. So the square root property is essentially the opposite of what we just saw in the last section. Essentially, the square root can undo a square. So that's the main takeaway here, but there is an extra step that we have to consider when using the square root property, and I'll demonstrate it in this first example. So like I said, we can use the square root property to essentially undo a square, kind of the opposite of what we just saw in the last several examples. So if I have x squared on one side of the equation and I want to completely isolate for x, so I want to solve for x, I'm just going to take the square root on both sides. That square root and the square are essentially going to cancel each other out, and I'm going to be left with x by itself on one side of the equation. And on the right-hand side, I'm going to have the square root of 225. But this is where that extra step comes into play. Whenever I take the square root or use the square root property, I'm going to actually have two solutions. Since notice this is a quadratic here, so I'm going to have two solutions. And my second solution is going to be the opposite of my first, and opposite in sign. Okay, and we'll see why in a moment. So the square root of 225, that's going to be 15. So I'm going to have x is equal to 15, or x is equal to -15, since I have that negative on the outside of my radical. So these are going to be my two solutions. My solution set is going to consist of x is equal to plus or minus 15. So that's how I'm going to write that here, plus or minus 15. Now the reason why we're going to have two solutions here, like I said, is because we're dealing with a quadratic. But let's go ahead and check our solutions to make sure that this makes sense. So if I want to check x is equal to 15 here, I'm just going to plug 15 into my original equation. So 15 squared is equal to 225, which is a true statement. All right, let's check our second solution here. X is equal to negative 15. Okay, I'm going to plug in negative 15 into my original equation here. And I'm going to get negative 15 squared is equal to 225, which is also a true statement since anything or a negative squared is always going to give us a positive. In fact, anything squared is always going to give us a positive. So this is why we have two solutions in our square root property. Okay, so keep that in mind whenever we're evaluating equations using the square root property. So let's go ahead and look at the second one. In this case, we have this guy. Now, right off the bat, we're not going to use that square root property yet, because if I take the square root of this and the square root of this side, this is going to be very complicated here. In fact, we don't want that radical. That's why we have the power rule that we saw in the last section. We're going to use the square root property once we have x squared completely isolated. So our first two steps then are going to be to isolate x squared. In order to do that, I'm going to first add 72 on both sides of my equation, and then I'm going to divide both sides by 3 to get that x squared completely by itself. Doing so, I'm going to get that x squared is equal to 24. All right, now from here, I'm going to go ahead and use that square root property. I'm going to take the square root on both sides of my equation here to get rid of that square in my x, but doing so, I'm going to end up with x is equal to positive 24, or x is equal to negative square root 20 of 24. All right, so these are our two solutions, but this is not going to be my final answer because this is not fully simplified. I know I can break 24 up into at least one factor, or I'll break it up into two factors where at least one of them is a perfect square. One of those is going to be 4. This is going to be the same thing as the square root of 4 times the square root of 6. And similarly on this side, but we just have that negative out in front. All right, so we're going to end up with x is equal to 2 square root 6, or x is equal to negative 2 square root 6. So our final answer is going to be the solution set of those two solutions, 2 root 6 or minus 2 root 6. So I'll use that same notation, plus or minus 2 root 6. So this would be our final answer here. Just like we've seen before, if you were to input, let's say, this answer here, positive or negative square root 24 into MyLab Math, it might mark you wrong here because these are not fully simplified. So just keep that in mind when you're solving these types of equations. All right, now for this last one here, we're going to do the same thing. But notice in this case, we don't just have an x squared, we actually have that this entire thing is being squared. So what we're going to do is go ahead and use that square root property right away. We're going to end up with this 2x plus 3 on the left-hand side of our equation because we took that square root of both sides, or on both sides. Then on the right-hand side, I'm going to have the square root of 25, but remember our square root property tells us that we're going to have two solutions. So I'm actually going to end up with two equations that I want to solve. I'm going to have 2x plus 3 is equal to positive, and 2x plus 3 is equal to negative square root 25. Okay, so from here, it becomes very similar to what we've seen before. We're going to have 2x plus 3 is equal to the square root of 25, which gives us 5. Or 2x plus 3 is going to be equal to negative square root of 5, or 25, which is 5. All right, so let's go ahead and solve both of these. I'm going to subtract 3 on both sides of my equation here. This is going to give me 2x is equal to 2. And on this other equation here, I'm going to subtract 3 on both sides. This is going to give me 2x is equal to negative 8. So we'll go ahead and continue on. This tells me x is equal to 1 by dividing by 2 on both sides, or x is equal to negative 4, again, by dividing by 2 on both sides of my equation. So in this case, the solution set is going to be x is equal to negative 4 and x is equal to positive 1. So this would be our final answer. Now for this next problem here, we're looking at an application problem. So we're told that the Gateway Arc in St. Louis, Missouri is 630 feet tall. We want to use Galileo's formula, distance is equal to 16 times t squared, to determine how long it would take an object to be dropped from the top of the arc to reach the ground. So in this case, like I said, this formula is distance is equal to 16 times t squared, where t is time. So we're given a distance of 630 feet tall, and we want to figure out how long it would take. So our distance is equal to 630. We're going to plug that into our formula. 630 is equal to 16t squared. So now it just becomes a matter of solving for t. This is what we're asked to find. So we'll go ahead and do that. Firstly, I'm going to divide both sides of the equation by 16 here so that we can get t squared completely isolated. Doing so, I'm going to end up with 630 divided by 16 is not a whole number, so we're going to go ahead and round it here. This is going to be approximately 39.375 is equal to t squared. Now that I have my equation of this form, I can use the square root property to get t completely alone, but we know that when we do that, we're going to end up with two solutions. So I'm going to have t is equal to the square root of 39.375, or t is equal to negative square root of 39.375. Now, in this case, we can go ahead and actually plug this into our calculator here. We're going to get that t is equal to, let's see, approximately 6.3, or t is equal to approximately negative 6.3. So these are our two solutions here. But remember, in the context of this problem, it's asking us how long it would take for an object to hit the ground if it's dropped from the top of this arc. Well, it wouldn't make sense for that time to be negative. So this would actually not be one of our solutions here. So this tells us that it would take the object about 6.3 seconds to reach the ground. So this would be our final answer. Let's say about 6.3 seconds. All right, so the last thing that we're going to look at in section 8.1 is solving quadratic equations by completing the square. So for this first one here, we're going to go ahead and complete the square. So if you haven't already done so, please go ahead and check out the textbook. There are some nice examples in there, but I've also pasted this for us. So this is a screenshot directly from our textbook on the four-step process to complete the square. So the first thing that we need to do is make sure the second degree term has coefficient 1. Well, going up to this guy here, the second degree term is m squared. It does have coefficient 1. So this tells us that we can proceed to step 2. Now for step 2, we want to be sure that the equation is in its correct form. So what we want is all of the variable terms on one side of the equation and the constant term on the other side. So going back up to our problem here, as you can see, that is not the case here. What we're going to have to do is add 32 to both sides of our equation because we want our variable terms by themselves. We're going to have m squared minus 4m is equal to positive 32. All right, now let's go to our next step. In step 3, we're actually doing the process of completing the square. The first thing that we want to do is take half the coefficient of the second degree term and square it. Whatever that value is, we're going to add it to each side of our equation. And our last step is going to be to factor the variable side. Once we've added this square that we found in the first two steps here, the left-hand side should be a perfect square trinomial, so it'll be nice to factor it. Lastly, what we want to do is combine terms on the other side and solve the equation using our square root property. So let's go ahead and do that. First things first, we want to take half the coefficient of the first degree term and square it. So let's do that on the side here. So this first coefficient here, or first degree coefficient, is going to be this negative 4. So we need to take half of negative 4 and square it. So I'm going to take half of negative 4 and square it. This value is going to give us negative 2 squared, which gives us 4. So this is the value that we're going to add on both sides of our equation. So I'm going to add 4 here and add 4 here. Upon doing that, I've turned the left-hand side of this equation into a perfect square trinomial. So this factors into, we're just going to end up with m minus 2 squared. And on the right-hand side, I'm going to end up with 36. So from here, I now have a nice equation that I can easily solve using the square root property. What I want to do is get rid of this square here. So I'm going to go ahead and take the square root on both sides of the equation to undo that square. I'm going to end up with m minus 2 is equal to the square root of 36. But remember with the square root property, we're going to have another solution. M minus 2 is going to be equal to negative square root 36. So from here, let's go ahead and solve for m. M minus 2 is going to be equal to 6, since the square root of 36 is 6. And we're going to have that m minus 2 is equal to negative square root 6, since that negative is on the outside of our radical. This tells us that m is going to be equal to positive 8, or m is going to be equal to negative 4. So our solution set in this instance is going to be negative 4, comma, 8. All right, so that's an example of completing the square with a quadratic equation where the second degree coefficient is 1. Now looking at this next one here for question 65, as we can see, the second degree term, the coefficient of the second degree term is not 1. So this is going to introduce an extra step in the process of completing the square. So let's go to our procedure here. If that coefficient is not 1, but some other non-zero number a, we're going to divide each side of the equation by a. So let's go ahead and do that here. Before we go ahead and divide both sides of the equation by this, though, there's actually an extra step that we need to do. We need to make sure that we have all of our variable terms on one side of the equation before we go ahead and divide it out. So we're going to add 2 to both sides of our equation here. We're going to end up with 2k squared plus 5k is equal to 2. And then now we're going to go ahead and divide out 2 on both sides of our equation. Now, technically, I guess we could have just divided by 2 right off the bat and then moved this constant over, but it's just kind of easier to do it this way. Either way, you'd end up with the same equation, the same resulting equation, which is going to be k squared plus 5k over 2 is equal to 1. All right, so let's go back to our procedure here. As we can see, um, the coefficient of the secondary term was not 1, so since it wasn't 1, we went ahead and divided by a. Then we kind of did step 2 first. We wrote it in the correct form first and then divided by a. Now in step 3, we want to go ahead and complete the square. So we're going to proceed like how we saw in the last example. We're going to take half the coefficient of the first degree term and square it. Well, the coefficient of this first degree term is going to be 5 over 2. So we're going to take half of this guy and square it. So if we want to take half of 5 over 2, that's the same thing as multiplying it by half here. Since we're dealing with fractions, it might just be easier to look at it this way. This is going to give us 5 over 4 squared, which is going to give us 25 over 16. Okay, so this 25 over 16 is the value that we're going to add to both sides of our equation. So making some room here, 25 over 16 and plus 25 over 16. We have to add it to both sides of our equation because remember, whatever we do to one side, we have to do to the other. All right, so now that we've done this, we've ended up with a perfect square trinomial on the left-hand side of our equation. Now, it might not be as obvious in this case because we're dealing with these fractions, but this is a perfect square trinomial, and if you're ever confused on what the value might be that we're going to be adding to our variable, it's always going to be what this number is. It's always going to be half of our coefficient for our first degree term. So in this case, we're going to add 5 over 4 to our k and then square it. So what I mean is, this is the same thing as k plus 5 over 4 squared. And on the right-hand side, we're going to have 1 plus 25 over 16. In order to add these guys together, we're going to need to get a common denominator. So just to recap, I know that this is going to be 5 over 4. If I went ahead and FOILed this out, if I took k plus 5 over 4 times k plus 5 over 4, I would end up with this perfect square trinomial here. But a little bit of a shortcut, especially when it's not as obvious, since we have these fractions here, is to look at half of our first degree coefficient. Whatever that value is going to end up being whatever this guy is. Okay? So just keep that in mind. But of course, we can always FOIL and make sure that we have the correct factored form. All right, let's go ahead and keep simplifying this. We're going to have k plus 5 over 4 squared on the left-hand side. And on the right-hand side, we're going to have 41 over 16. Now we can use our square root property. We're going to take the square root of both sides of our equation. We're going to end up with k plus 5 over 4 is going to be equal to positive square root of 41 over 16, or the negative version. All right, so let's go ahead and isolate our variable k then. We're going to subtract 5 over 4 on both sides of our equation for both of these. All right, doing so, we're going to end up with minus 5 over 4 plus the square root of 41 over 16. This is going to be our first equation here. Then our second one is going to be the opposite of this. So minus 5 over 4 minus the square root of 41 over 16. Now we can go ahead and keep simplifying this here. Using our quotient rule for these two fractions, we're taking the square root of this quotient. So that's going to be the same thing as taking the square root of our numerator and denominator separately. So we're going to end up with minus 5 over 4 plus the square root of 41 over the square root of 16, which is also just 4. Similarly, we're going to have minus 5 over 4 minus the square root of 41 over the square root of 16, which again, oops, is 4. All right, so this would be our final answer here. I'm going to go ahead and move that down so we have more space. Notice that for both of these equations here, though, both of these fractions have a denominator of 4. So I can write this as, in our solution set, I'm going to have negative 5 plus the square root of 41 over 4. And negative 5 minus the square root of 41 over 4. So these are going to be our two solutions here. And then something else to note is that I could have written this as plus or minus. So I could have minus 5 plus or minus the square root of 41 over 4. Either way would be correct. So that would be our final answer.